Hey everyone, it's Ryan from Smart Edition Academy, and today we're going to go through the HESI A2 chemistry practice test. You can take this free practice test with me by using the link in the description. I will go through each question one by one to explain the correct answer. Starting off, why must researchers consider the placebo effect? So, the correct answer would be to account for the body's response to fake treatments. It may help to think of what the placebo effect actually is. In essence, a placebo is something that is given to a patient or a test subject that is not the drug of interest. It could be a sugar pill or even a different drug, but the main point is that it is not going to elicit the effect we are looking for. It is used in trials like double blinds to make sure that the drug or whatever chemical we're testing actually gives the response we are looking for. So it proves validity for certain experiments. So that's one way to remember why a placebo effect accounts for body's response to a fake treatment. Next up, what step of the scientific method relies on logic, reasoning to be formulated? This would be developing a hypothesis. Again, thinking of what a hypothesis is, it's really just a question that has a proposed answer and possibly even some reasoning with it. It is the first thing that must be used in the scientific method. And as a helpful tip with this one, a lot of hypotheses come in if, then, because format. So if would be the actual thing that's being looked at, then would be what we assume is going to happen, and because is going to be the reasoning why. For instance, if a plant is given more light, then it'll grow larger because it has more opportunities to grow. So thinking of all this, it really requires a lot of logic and reasoning to actually be formulated. And in comparison to the others, asking a question, researching information, those really just involve actually acting, not using logic or reasoning to formulate something new. Next, which term is used interchangeably with negative variation? The correct answer to this question would be inverse correlation. Although this one may be kind of backwards to think about, inverse correlation would be the correct answer. It can help to think of positive variation as a deviation or movement in data that goes in the same direction as something else. It is positively correlated. Vice versa, negative variation would be the opposite, or inversely correlated to something. Thus, inverse correlation is another term for negative variation. Next, what measuring tools are being used? We can see here that there's some large tube holding a liquid with what we can assume to be measuring marks, and there's a smaller tube with larger marks and a red substance. We can probably assume that this smaller tube here is a thermometer, which is used to test the temperature of a certain substance. It is being suspended in a larger vessel here, which would be a graduated cylinder, so this would be the correct answer. To rule out the other answers, a ruler is usually used to measure length, and we are probably familiar with those, so that is not being shown here. Additionally, a barometer is usually a closed vessel that is used to measure pressure, which isn't happening here. Next, light travels at the speed of almost 3 times 10 to the 5th kilometers per second. How is this value written in standard notation? Standard notation is what we usually see. However, scientific notation, this 3 times 10 to the 5th, is a format that is often used in science to simplify numbers so they are easily read, for instance, in a scientific paper. Understanding both of these can help you in being able to transfer between both of them when you're given a number in either scientific or standard notation. In essence, scientific notation just takes all the zeros that we don't need to see and turns them into an exponent times 10. So if it is a positive exponent, the decimal would be moving to the right, making the number larger. If it is a negative exponent, the decimal would be moving to the left, making the actual number smaller than we think. So for this, we can see the 3, and it's being multiplied by 10 to the 5, which essentially means we would add 5 zeros. 3, 4, 5, and that shows that we have 300,000 kilometers per second would be the answer. Next, which of the following statements describes the mass of an electron? The correct answer is the mass of an electron is less than the mass of a proton or neutron. Thinking to what an atom looks like, it has a central core composed of neutrons and protons in tightly packed bundles, and it has outer cloud of electrons flying between. In essence, the electron is the smallest portion and it is incredibly tiny and flies all around, whereas the protons and neutrons really just stay in the middle and they're bigger than the other things. There's not a great way to remember this or think of it, or even reasoning. However, I like to think that the electron is negatively charged, and its mass is almost so small that it is a negative number. So you can remember that it has the smallest mass of all the components of an atom. Next, which of the following parts of an atom takes up the most space in terms of area? This one's a hard one to think about, but the correct answer would be the electron cloud. Going along with the last example of thinking about the atom, there's the central area, and a lot of students like to think that that is the biggest part because it just is a clump of neutrons and protons that takes up a good amount of space. Even though the electrons are the smallest component, they actually travel a far distance in orbitals outside. If we think of this as the nucleus of an atom, it's pretty big. However, the electrons travel far out in these orbitals and actually take up the most space in an electron cloud, making them the biggest in terms of area. A neutral atom of aluminum has 13 electrons. How many electrons can be found in each shell in the electron cloud? Thinking of orbitals, the first shell can usually contain 2 valence electrons, and the other shells can contain 8 respectively. We only need to know up to the third shell in this case. With 13 electrons, they all must start from the first shell going outward. Thus, 2 would be used in the first, 8 would be used in the second to fully fill it, and a final 3 that is found in the 13. This adds up to 13, would be found in the third shell. So, the answer would be 2 in the first shell, 8 in the second shell, and 3 in the third shell. Which of the following is a part of the metric system? This one, the answer would be Celsius. If you're an American, you're probably familiar with feet, pounds, or even ounces. These are all typical measurements that are used in America, not much elsewhere, and they are not a part of the metric system. Celsius, however, is. What is the Celsius value for 85 Kelvin? This really comes down to a simple equation that is often used in chemistry that uses the relationship of Kelvin and Celsius together. The relationship is equal to Kelvin is equal to Celsius in degrees plus 273.15. As we can see in this equation, it's really simple if you're given Kelvin to solve for Celsius, or if you're given Celsius to solve for Kelvin. In this example, we're given Kelvin. So 85 Kelvin would be equal to Celsius plus 273.15. If we isolate and subtract 273.15 from both sides, so we get Celsius alone, we would get that Celsius is equal to negative 188, rounded up. Next question. A patient has a fever of 105 degrees Celsius. What is this value in Fahrenheit? Again, this relies on a simple equation that involves the relationship of Celsius to Fahrenheit. The equation is Fahrenheit equals Celsius times 9/5 plus 32 degrees. So, since we are given Celsius here, we can use it to solve for Fahrenheit. Fairly easy. So when plugged in, we would get that 105 times 9/5 plus 32 is equal to Fahrenheit. And in the end, that answer would be 221. Next question, what is the temperature of 35 degrees Celsius in Kelvin? Just like the last questions, this one also uses the relationship of two temperature measurements. So again, the equation we'd want is Kelvin is equal to 273.15 plus Celsius. In this example, we're given the degrees in Celsius, which makes this fairly simple. So we can just add them together. 35 degrees right here, and Kelvin would be equal to 308. Next, given the heating curve of iron, what are the approximate melting and boiling points? As we can see in this graph, it shows the time on the x-axis versus temperature on the y-axis in Celsius. That's pretty important. So we can see that there is a large spike and then kind of a plateau right here, and then another large spike and a plateau again, and then another large spike. Let's focus on these plateaus and talk a bit about the chemical characteristics of melting and boiling points. We can think of the process of turning from a solid, which would be all the way here, to a gas, which is here, as a continuous spectrum. A chemical doesn't really stop and start from here to there. It wouldn't be a continuous line. And the process of melting or boiling, which are indicated by these plateaus, is pretty intensive and requires a lot of heat and energy to actually occur. Thus, the process of turning from any state of matter has a period of plateau in which the chemical is actually stable, and after a certain amount of energy is put in, or pressure, it would finally flip up and go to the next state. So in this graph, this would be a solid, we'd come to the melting point here, turning it into a liquid, and we'd come to the boiling point at this plateau, turning into a gas. So, going to the temperature axis here, we can see that the melting point would be 1500 degrees Celsius, and the boiling point would be roughly 2900 degrees Celsius. Next question. Compare the boiling points of alcohols in the table below. Molecules of these alcohols are similar, but they have a different number of carbon atoms in the chain, and, therefore, different masses. Based on the boiling point data of the table, what conclusion can be drawn about the relationship of these number of carbon atoms in a molecule and the interaction of the molecules? As we can see here, we have a bunch of different carbon species right here, showing their mass, which is increasing with the number of carbon, which is expected, and the boiling point, which is increasing, which is pretty interesting. This all really comes down to intermolecular forces, which is the willingness for molecules to actually stick together and interact. And this dictates whether things are solid at room temperature, whether they're liquid, whether they're viscous. It really rules everything within the realm of chemistry. In terms of intermolecular forces, hydrogen bonding occurs a lot with OH species such as these. However, since they all have the same amount of OH, that's pretty negligible. We really want to focus on the increasing carbons, not so much the hydrogens. Hydrogens are smaller and they don't have many attractive forces, but carbons will increase the size and mass of a molecule. So, as a molecule increases, we can think of it, small molecules, this would be the one carbon molecules, can interact only on the surface area of that carbon. So they can connect here, 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 and they have decent interactions. However, when a molecule, such as 4 carbon, would be in a log shape, more like this, and they'd have more surface area to interact, this is also correlated to their mass and size. When they interact like this, the boiling point would increase because you have to break all of these interactions in order to separate the molecules. Thus, we can deduce as the number of carbon atoms increases, the strength of the intermolecular forces between the particles increase. And that is shown here, because as the mass and the carbons are increasing, the boiling point increases. Next up, a student is recording the temperature of a solid substance as he heats it over a Bunsen burner and notices that the temperature stays constant at 62 degrees Celsius for 4 minutes. How can the substance be described during these 4 minutes? The correct answer would be, it is melting. We can think back to that question showing the heating graph of aluminum. In that question, we saw that when a substance is boiling or melting, it reaches a plateau point where energy is being put in, but it doesn't quite want to go to the next stage. Given this story, we can see that it is constantly being heated, however the temperature is staying constant. Just like in that graph, that would show that it is in one of those stages of change. However, we can deduce, since it starts off as a solid substance, the change that would occur first would be melting. Next up, flammability is an example of what? Flammability would be an example of a chemical property. We can really rule out polar substance and weak substance. Those are just descriptions of what a chemical has, not exactly what it does or what it is like. A lot of students want to think of physical properties when it comes to flammability. However, a physical property would be something like density, molecular weight, and things like that. Chemical properties really are the interactions of chemicals with each other. In chemistry, there is a famous type of reaction, really popular, called a combustion reaction, and that is when one species, we can call it X, interacts with oxygen to form carbon dioxide. This is what we would basically call being on fire, and that is the flammability of a compound. Although it may not seem like it, flammability is a chemical reaction, so it would be a chemical property. Blank is the diffusion of water molecules through a membrane in the direction of higher solute concentration. The answer to this one would be osmosis. Osmosis simply is the movement of water, and it is normally in a diffusion gradient of high to low. So that can be high pressure to low pressure, high solutes to low solutes. However, with water, osmosis is the movement of water, plain and simple. It may be best to weed out the other answers in this case if you can't remember osmosis specifically. Melting is pretty simple. That is the process of a solid turning into a liquid. That wouldn't be the diffusion of water. Polarity is simply when a molecule has two distinct parts, usually in terms of electronegativity or the willingness to bond or pair with electrons. Sublimation is the process of a solid forming directly into a gas, which again wouldn't be the diffusion of water. Osmosis really comes down to a biological knowledge, so this one you really just want to nail in what osmosis means, and it is the diffusion of water. Next up, in the Lewis structure for carbon dioxide shown below, how many electrons is the carbon atom sharing with one oxygen atom? Carbon dioxide right here. And we can see that it is bonding with two oxygens, but we are really just interested in one. When an atom shares electrons with another, it really just shares one, and it would share another with the other molecule. So for instance, this oxygen is giving one atom here and one atom here. And this carbon is giving one atom here and one atom here, forming bonds each, such as that. We can really simplify it with dots if that helps you think about it. With this, we can see between one oxygen, we can focus on here, there'd be 1, 2, 3, 4 atoms. With this oxygen, we can focus on just it. There'd be 1, 2, 3, 4 electrons being shared in these bonds, in a double bond. In a single bond, there are 2 electrons being shared, and we can just double that to show there are double bonds. Again, the answer would be 4. Moving on. Consider the carbon-carbon bonds that exist in the molecules shown below. Which of the compounds contains the strongest carbon-carbon bond? For these, we really just want to focus on the interactions of the main central carbons here. We can rule out that any carbon that is not bonding with a carbon, such as methanol, is not going to be the answer. Additionally, a single bond isn't that strong. This one also isn't bonding with a carbon, so it's probably not going to be the answer. Then it really just comes down to understanding what bonds are. We can really think of bonds as like a rope or a rubber band that is tying 2 atoms together. With a single bond, the band is pretty tight, but if you include more bands, it would get even tighter and tighter, and the bonds would increase and the size between them would decrease, and the atoms would be pulled together tighter and tighter and tighter. Thus, as you increase the amount of bonds, you increase the amount of attractive forces between the two. So the more bonds, and here we can see there's a triple bond compared to a double, would have the strongest carbon-carbon bond. So in this case, acetylene would be the correct answer. According to the Lewis structure below, what is the formula for methanol? Given a full Lewis structure, we can really just add up the number of elements. In most carbon, hydrogen, oxygen species, such as glucose, C6H12O6, we really like to give the format of C, X, H, X, O, X. It's standard, and it lets us know how many of each element are in it in a way that anyone can understand. So, counting out methanol, we can see that there is a 1C. It doesn't need any subscript here. We can also see that there are 1, 2, 3, 4 hydrogens and 1 oxygen. So, it would be CH4O. And we can see that there is a CH4O. Next up, in which reaction are both the reactants and the products heterogeneous mixtures? Heterogeneous really just means that the substances that are in the mixture are a different state of matter, or just different similarly. So, we are looking for things that come in different states in the mixtures. Since this is just one mixture, and this has two things in the same state, it would not be correct. Additionally, here we can also see that both species in each mixture, the reactants and the products, are all the same again, so this is not correct. Moving down, we can see in these products, they are heterogeneous because there's a solid and an aqueous forming a mixture. However, the reactants are both aqueous, so this would not be correct. In this, both the reactants have aqueous and solid, they're different or heterogeneous, and the products are also a solid and aqueous or heterogeneous. So the correct answer would be this silver compound, the third option. In the following single replacement reaction, blank replaces blank. In replacement reactions, we can really just think of one element taking the place of another. You can get complicated and look at charges, so you can see, for example, chlorine is normally negative and iodine is negative, so they can pretty much fill the same role. However, you can also just look at the differences between the reactants and the products. Here, I like to focus on the biggest species first, such as this NaI. We can see in the reactants, it is NaI. However, in the products, it is NaCl. So we can assume that this chlorine swapped places with the iodine. So the iodine in the products is all alone, just like the chlorine was, and the chlorine is paired with sodium, just like the iodine was. So we can see that chlorine ended up replacing iodine. Next up, what solution has a pH of 7? Thinking of the pH scale, the lower you go down, so the lowest normally is 1, would be acidic. We can think of things like lemon or even battery acid, and then you go to the middle, which is 7, which is neutral. I'll abbreviate it there. And then 14 would be the basic side of things. So that would be things like bleach or even ammonia. So the 7 is neutral, and that is what we're interested in. So neutral things in the grand scheme are pretty basic, for lack of a better term. They don't interact with a lot in terms of being acid or base. They don't donate any protons, they don't want to take any in, and they don't have a lot of those really violent reactions that we see. And if you know some basic chemicals, you can probably tell sodium hydroxide, and that's really basic. Pyridine is also a base. You can think of that in terms of biology, looking at pyridine bases. But really the correct answer here would be pure water. We can think of pure water, that's something that we can drink. It's not acidic, it's not basic. It is simply neutral. Next up, an acid that dissociates into hydrogen ions is defined as a. The answer to this would be Arrhenius acid. This one, you really just have to understand some of the basic definitions that have been through time, and those would be things such as the Bronsted-Lowry or an Arrhenius. We can rule out weak acid. Weak acid is just a way to define how strong an acid is relatively on the pH scale. Additionally, conjugate acid would be ruled out as well. Conjugate acid is what is formed when a base reacts with an acid to take on protons, and it basically turns into a weak acid. Getting down into the weeds, a Bronsted-Lowry acid is one that donates protons, not necessarily specifically hydrogen protons. Thus, if we're specifically looking at hydrogen ions, that would be the definition of an Arrhenius acid. Lastly, what is the conjugate base of sulfuric acid? Again, a conjugate base is what is formed after an acid has a reaction, usually with a base. So, thinking of sulfuric acid, the formula is H2SO4. And if it reacts with a base, we can just use a really strong example here, such as sodium hydroxide. It would donate one of these protons to sodium hydroxide to essentially form water plus NaHSO4. And this OH here bonds with this H to form the water, and this bonds with that. Now, I'll write it again here. We don't see an NaH. I'll write it again here. We don't actually see an NaHSO4. That is because Na is a spectator ion. It basically is used to balance the charge of this. Thus, if we take out the Na, which is positive, we would have a negative overall charge, and the answer would be HSO4-. To reiterate, if you want to form a conjugate base of an acid, you can simply imagine getting rid of one of the protons it has. So for example, here, if I write it again, H2SO4, that's sulfuric acid. If we got rid of a hydrogen, it would be left as HSO4. And hydrogens are positive, so the overall charge would be 1 negative, again, leading us to HSO4-. Okay, that is it, guys. Great job for following along. Be sure to check out the link in the description below for the entire free HESI A2 practice test and additional study resources such as the HESI study group and the HESI online course. Good luck with all your studying.